To deliver the welcome address, I invite Engineer Posala Amradenia, President-elect, as our President Engineer Daniel Jayalat is overseas. Over to you, sir. President-elect.
Our guest speaker today, Engineer Dr. S.K. Navaratnaraja, Senior Lecturer, Department of Civil Engineering, University of Moratuwa. University of Pereira. Past Presidents, Vice Presidents, Council Members, Head of the Department, Civil Engineering, University of Pereira, Chairman of the Civil Engineering Sectional Committee and Committee Members, family members of late Professor E.O.E. Pereira, members of the institution who are joining online and present here, CEO, Executive Secretary, staff members of ISL, ladies and gentlemen. Very good evening to you. The Institution of Engineers Sri Lanka, as the premier professional body for engineers in the country, takes the pride in commemorating the distinguished persons who have rendered invaluable service to the nation through their expertise and vision. Among them, Engineer Professor E.O.E. Pereira stands out as a towering figure in the history of engineering in Sri Lanka. Within our community, he is rightfully recognized as the father of engineering education in Sri Lanka. It was through his foresight and dedication that a strong foundation of engineering education was established, enabling generations of engineers to serve our nation. Indeed, many of us would not be here today as professional engineers, but if it was not for his extraordinary sacrifice and contribution. At this point, it's my great pleasure to extend a warm welcome to our distinguished speaker this evening, Engineer Dr. S.K. Navaratnaraja, Senior Lecturer in the Department of Civil Engineering, University of Pereira. We eagerly looking forward to hearing the valuable insight on advancing rail track technology. I also take this opportunity to warmly welcome Council past presidents, Council members, family members of Professor E.O.E. Pereira, our members, and all invitees. As a tradition, it's now my privileged duty. It is my privilege and duty to say a few words in remembrance of late Engineer Professor E.O.E. Pereira. Professor E.O.E. Pereira was born in 13 September 1907 and received his education at the Royal College, Colombo, where he excelled in both academic and sports. He won the Soisa Science Prize, Muhammad Ali Arithmetic Prize, Evans Prize for Mathematics while schooling. In 1928, he entered the University College, Colombo, and graduated with first-class honors degree from the University of London, gaining first place in the Faculty of Science and winning the engineering scholarship. The scholarship enabled him to enter Downing College, Cambridge, where he gained the distinction of being the only graduate who finished the 3-year degree in 2 years. From the University of Cambridge, he graduated with a first-class honors in mechanical science in 1931. He served in the Department of Public Works for 15 years before joining teaching staff of University of Ceylon in 1946. Professor E.O.E. Pereira was responsible for putting in place the foundation on which higher education in engineering in Sri Lanka is built up on today. Called upon to provide leadership when the country decided to educate the engineers in its own soil, he had to literally start from scratch in establishing the first faculty of engineering in the country. At first, in temporary setting, starting at Colombo Technical College at Maradana, and then in a shed at Thurston Road premises of now University of Colombo before it found permanent accommodation at Pereira University. The fact that the University of London decided to withdraw the external BSc engineering degree being conducted up to that time at the Ceylon Technical College. Not only he did have to hurry scrambling the necessary university staff, but also to attend to acquiring of most appropriate equipment for the laboratory that was being built at the new facility, while also overcoming the administrative hurdles thrown across him in his path. That he achieved his goal successfully and appointed as the Dean of the Engineering Faculty for 2 decades before being appointed Vice Chancellor of the university, which speaks volume of his greatness. Professor E.O. Pereira was honored with the title Vidyajyoti in 1986. The E.O. Pereira Theatre of the Faculty of Engineering, University of Pereira was named to honor him, and several awards were made each year in his name. The annual E.O. Pereira Memorial Prize is awarded for the best paper by the Institution of Engineers Sri Lanka, and the E.O. Pereira Gold Medal at the Faculty of Engineering, University of Pereira. He passed away in 1988. Engineering education today faces many challenges. It must not only impart knowledge, but also cultivate the right skills, attitude, and values that contribute to the sustainable and inclusive growth, while ensuring the preservation of our environment. At the same time, it must remain agile and responsive to the rapid technological advancement, particularly in the era where artificial intelligence is increasingly taking over routine decision-making process and operations once performed by human. With this introduction, it's now my privilege to warmly invite our distinguished speaker to deliver this year's memorial oration. So over to you.
Thank you, President-elect. Let me have the privilege of introducing our speaker today. Dr. S.K. Navaratna Raja is currently a senior lecturer and postgraduate coordinator of Geotechnical Engineering program in the Department of Civil Engineering at the University of Pereira, where he has served since 2012. He earned his PhD from the University of Wollongong, Australia in year 2017, Masters in Civil Engineering from the University of Oklahoma in year 2006, and a first class honors BSc Engineering from the University of Pereira in year 2001. He worked as a geotechnical engineer at Group Delta Consultants, California from 2006 to 2012 before joining the University of Pereira. His professional credentials include Associate Member of the Institution of Engineers Sri Lanka, a registered professional engineer in the state of California, USA. Navaratna Raja's research focuses on transport geotechnics, problematic soils, ground improvement, stability of geotechnical structures, and numerical methods in geotechnical engineering. He has published more than 50 articles in high-impact international journals and peer-reviewed conference proceedings. In year 2023, he received the prestigious, to be safe side, I will call it this way, MV Award, the ICE UK Award for Best Overseas Paper on Ground Improvement using Waste Materials, published in the ICE Journal of Ground Improvement. SMV stands for Sir Mokshagundam Visvaraya Award. I hope it is correct. He was also a recipient of the President's Award for Scientific Research in year 2018 by the National Research Council of Sri Lanka for a paper published in the ASCII Journal of Geotechnical and Geoenvironmental Engineering. In 2016, he received Engineering Excellence Award of IESL, New South Wales Chapter, Australia, among many other awards. I warmly invite you to be with us.
Thank you very much, sir, for the kind introduction. Good evening, distinguished guest. Engineer Granny R. Jailath, President IESL. Engineer Kosala Kamrudiniya, President-elect of IESL. Engineer Mangala Silva, Chair of the Civil Engineering Sectional Committee. Engineer Suran Fernando, Honorary Secretary. Engineer Manjula Samarasinghe, Honorary Treasurer. Engineer Professor Ranjit Isanayaka, immediate past President. Vice Presidents and Council members, all the past Presidents. Mr. Lawrence Pereira, son of late Professor E.O.E. Pereira, and their family members, relatives, and friends of late Professor E.O.E. Pereira. Engineer Professor Kusan Vijay Sundara, Head of the Department of Civil Engineering, University of Peradeniya. Members of the Civil Engineering Sectional Committee, engineers, all members of IESL, Engineer Neil Abesegara, CEO of IESL, and staff of the IESL, my colleagues from the Faculty of Engineering, University of Peradeniya, and all the distinguished invitees, both those who are present here and also joining virtually in the Zoom. It is indeed a great honor for me to deliver the Engineer Professor E.O.E. Pereira Memorial Oration 2025. I wish to sincerely thank the Institute of Engineers Sri Lanka, the President and the Civil Engineering Sectional Committee, and in particular Dean of the Faculty of Engineering, University of Peradeniya, for nominating me and for organizing this event today. As members of the academic and engineering communities, we extend our sincere gratitude to our institution for commemorating the legacy of the late Professor E.O.E. Pereira, widely regarded as the father of the modern engineering education in Sri Lanka, through this annual memorial oration. This year's event is particularly significant as it is coincide with not only with this 118th anniversary of his birth, but also with the 75th Diamond Jubilee of the Faculty of Engineering, which he was instrumental in founding. At the commencement of this oration, I would like to take a moment to reflect on the endurance legacy of Professor E.O.E. Pereira, whose visionary leadership and unwavering commitment laid the foundation for the advancement of engineering education in Sri Lanka as we know it today. Today, as we gather to honor the memory of the engineer Professor E.O.E. Pereira, we reflect upon the life and the legacy of visionary who not only founded the Faculty of Engineering, but also dedicated himself to shaping the distinguished institution it is today. His efforts extended far beyond the mere establishment of the faculty. He was in essence laying the foundations for the future of engineering education in Sri Lanka. Professor Pereira envisioned a faculty that would serve not only the immediate needs of his time, but also endure as a beacon of academic excellence for the generations to come. He championed the creations of an institution equipped with the spacious lecture halls, state-of-the-art laboratories, and architecturally significant buildings that embodied both scholarly ambitions and national pride. In 1957, when he was asked to scale down his specification for the infrastructure and equipment, he chose to tender his resignation rather than compromise on his vision. This singular act of integrity and courage came to define his character and unwavering commitments. Had Professor Pereira yielded to external pressure, our faculty would not today stand as a symbol of prestige among university institutions in this country. Nor would Sri Lanka have been able to cultivate and produce the vast cadre of engineers who now serve both national and beyond. Professor Pereira was without question a brilliant academic and exceptional educator, and above all, a visionary leader whose enduring legacy continues to inspire all of us. I would like to echo a sentiment eloquently articulated by Dr. Jivananda Kirtisena, one of my University of Pereira, leader. He understood the needs of the rural students better than any other academic in the university. He consistently attuned to the challenges faced by students from rural backgrounds and actively fostered opportunities for their advancement. As someone who was raised in rural tea estate, where both my parents were employed as tea estate laborers, I have personally experienced the profound impact of such opportunities. It is my true foresight of Professor Pereira and the strength of our nation's free education system that a child from such modest beginning could rise to become an engineer and a university academic. I am therefore deeply humbled and profoundly honored to deliver the engineer Professor E.O.E. Pereira Memorial Oration today, as we commemorate the 118th birth anniversary of extraordinary pioneer, widely regarded as the father of modern engineering education in Sri Lanka. Again, this occasion holds even greater significance and joy as it coincides with 75th Diamond Jubilee anniversary of the Faculty of Engineering, University of Pereira. Today for this oration, my topic is advancing rail track technology from practice to innovation. I was trained at the University of Wollongong under Professor Buddhi Mahindra Ratna, one of the world leading expert in railway geotechnics. He was my PhD supervisor. For the past 12 years, after I get the training from the Australia, we have been doing a lot of research related to railway engineering. So the presentation or the work that I will be sharing with you today is the work of mine from the Australia, and also extending that to the University of Pereira for the past 12 years. I will give a brief overview of current Sri Lankan rail networks before I start to go to my research area. We have altogether 9 different rail networks. Some of these rail networks are already in extending, upgrading to the speeds. So many works going on in the recent past. Altogether, we have 1,561 kilometers of rail tracks, operates approximately 396 trains, including 67 long distance and 67 long distance and 16 intercity trains. Carries about 3.72 million passengers daily, and we have speeds from 25 to 40 kilometers in the hill country where I come from, and 65 to 70 in the low country, and it is near like 100 kilometers per hour in the northern upgraded line. If I take a quick key informations of rail track, we have a broad gauge system, 1,676 millimeter broad gauge, which is basically adapted during the British colonial era, in line with the Indian railway practice. And our design speeds are about 120 kilometers per hour, but basically permissible speed about 100 kilometers per hour. Originally, these sleepers used in this rail tracks are from hardwood sleepers, from teak, kumbuk, and jack type of trees. And in recent time, we have been using pre-stressed concrete in most of the areas. The ballast, which is my key area that I will be sharing the research today, it is traditionally rock material, gneiss, granite, biotite. Those are the parent rock material that we are getting for the ballast, typically 20 to 63 millimeter in size. The gradation that we are using is basically adapting from Indian standard with some adaptation made using the BS sieve sizes. And the ballast thickness vary from 200 to 300 millimeter depending on the class of lines. And we have this formation either made specifically for weak soils or a natural ground, transferring these superstructures load. At the track maintenance, we generally carried out, these are carried out by the Sri Lankan Railways through both manual gangs and the limited mechanized equipments, which are damping machines and using ballast regulators. At the present, we have nationally carrying about 5% passengers and 1% freight transport out of all this transport system in this country. So this clearly shows that there is significant need for railway infrastructure development. Let me give this the material, this ballast, which is one of the key element in the railway track system. And we also know that this railway transport system is one of the most popular mode of transport system in not only in in many parts of the Asia and in all over the world. There are many advantages we are having against this road transport, and this special material, this ballast material, it's a traditionally used material. So this ballast railway system is the widely used system in all over the world. There are key advantages on this using this ballast material, which is the main load bearing material. It is the one transferring the load from the sleepers to the underlying formations, minimizing the growth of vegetations, provide very good drainage, and also provide lateral resistance. So this is one of the key elements in rail track system. As rail networks evolve to support higher speed and heavier loads, that's what we are looking at to improving this railway system here. And also looking at the greater sustainability, enhancing this foundation system through innovative research-driven solutions become essential. So we need to do something to improve our system. So for today, I have a number of topics that I will be sharing based on our research and the innovations, from academic research to innovative industry applications, starting with this ballast gradation for Sri Lanka rail tracks, and impacts of fouling and shear fouling on the shear, degradation and permeability of ballast, artificial inclusions used in rail track, something like undersleeper pad, under ballast mat, and shredded rubber. These are the material used to stabilize the rail track. And sleeper ballast interface shear resistant, and which we are come up with a new material. We have applied a patent also for that. And criterion for predicting the track maintenance. And lastly, the impact of ballast shapes on the shear and degradation using a discrete element model and artificial neural network approach. So starting with, before I go into that each and every topic, I just wanted to let others know that at the Department of Civil Engineering, University of Pereira, we have built a state-of-the-art large-scale testing facilities in the recent past, for the past 5-6 years. The first machine, you can see the large-scale dynamic actuator, where you can test a real rail track in the laboratory. The rail track underneath this machine is a unit cell rail track, actual rail track. So we can laboratory. The second equipment we custom built at the department is a direct shear apparatus, where we can test full size ballast material. And again, the third one is the large scale constant head permeability apparatus, where we can do this full size material testing. These type of large scale testing apparatus are very, very important for this type of railway material testing, because this this ballast material, post granular material size ranges from 20 to 65, where this traditional testing equipment won't fit to these material sizes. So we need to either downgrade the size, something like a parallel gradation, or we have to go for a large scale apparatus. Downgrading with the size, with the parallel gradation, give a lot of limitations. So we thought of like, based on the experience I gathered in the University of Wollongong, Australia, for the last 6 years, we have been building this piece of equipments where we can test many different things about the railways. So the first title, the gradation of the Sri Lankan tracks. See the particle size distribution, the coarse granular material used in rail track are to give the shear strength of the track when the train is passing through the track. So it is a very good material for the shear strength. But until now, we are practicing with these Indian standard gradations, which is adapted from that system. And we are changing a little bit of with the BS sieve sizes. And the ballast particle, as I already said, is ranging from 19 to 63. You can see the ballast gradations of various countries, like, how they are using this, shows that like, different range. But we don't have a ballast gradation for Sri Lanka, and we are using the Indian standard gradation. So considering that, in our project team come up with a plan to why not we produce our own gradation. For that, we have collected, this is an ongoing project. We have so far collected materials from 7 places where this is supplying the ballast material to the railway system in Sri Lanka. We have collected the material and testing most of the site, and still there are a few more sites we tested. And at this time, I just wanted to thank Engineer Nuan Amarasena and Engineer Mohammed Jusafi at the SLR for supporting to get this material, and also the district engineers of these different places and the managers for getting this material to our laboratories. So these we wanted to check the gradation little outside the Indian gradations to check whether is there any better gradation that we can adopt. So we consider 3 different gradations. We consider one at the middle of this Indian gradation range and 2 outside the range. The one outside the range, we increase the smaller size the particle, where the one in the other side, we increase the large size particle. So there are 3 different gradations, and we use this material to test in our large scale testing apparatus. You can see here, you can see like it's, there are, we are coloring the ballast particles. That is because, after the testing, we wanted to analyze these particles, how these particles are degraded. So the different layers, we are putting a different colors, so that after the test, we can separate based on the color, and we can analyze how much the material degraded or break during this, direct shear testing. So this is our large scale testing apparatus, and we tested, all these 7 sites. And here I have, given one side from the well ballast sample side. This shows this shear and the degradation results. And based on these findings, and we come up with this conclusion, this PST3, which is we are having larger amount of larger size particle, which is performing better than the Indian gradation limit, and also the smaller particle that the other side we check. So not only this shear, it is enhancing the shear, and also it reduces this ballast degradations. So ballast degradation is one of the key parameter which decide how frequently you need to do your track maintenance. So reducing the ballast degradation is one advantage where you can delay the maintenance work and save money and time. So as I said, this project is an ongoing project. Still, we have to test more material from the side. And not only the shear test, we have to do the permeability test also for this material. Even though these coarse granular materials are good in permeability, there is one other item that I will be discussing here, the ballast fouling. When the ballast get fouled, the permeability is a problem. So we need to check for different gradation what happened when the ballast is fouling. What is ballast fouling? Ballast fouling is whatever the foreign material get into this ballast, the layer. Basically, the material size goes beyond less than 9.5 millimeter sieve is called as a foul material. These come from many different sources. Particle from abrasion, cone breakage, and splitting of this existing ballast particle while the train is in service, and infiltration of fine foreign particles from the track surface, especially during the coal transport. This is a biggest problem in Australian rail track, because coal always spill in the rail track and contaminated the ballast layer. Subballast and the subgrade infiltration by pumping and of fines from the sublayers, especially in the coastal areas. When the train is running cyclic load, pump this fine underneath layer and come and contaminate this ballast layer. And also, in some level, the slipper, concrete slipper also wear and, contaminate the ballast, and particle washed out from the water. Specifically, this type of problems are prominent in hill country tracks. And also wind blown sand particles near desert and beaches area. That is also, one way that ballast get fouled. And we mimic this type of ballast fouling in the laboratory by adding this different type of foreign materials, quarry dust, sand foul ballast, clay foul ballast, and we check this the shear and the permeability behavior of this ballast. And we come to a conclusion. We generally found that the fresh ballast are very good in shear. But when it is contaminated with especially clay and sand, it compromises the shear strength. Even though this ballast is showing like a little higher shear strength, that is because of this where this quarry dust is coming from is having a higher strength. So we are having a higher shear strength. But generally, this foul material is, compromising this the shear strength. So we have to be very careful on on this type of ballast getting fouled. Now we know that the ballast, getting fouled this material. We wanted to find a solution for that one, like, how we can help these railway engineers to clean or maintain their tracks, whenever this ballast fouling is happening. For that, we have started one study by checking the void contamination index, how much of a void in the ballast layer based on this, the method proposed by Indraratna et al. 2010. We come up with this, the void contamination index to calculate like how much of a layer is contaminated. So once this contaminated and we calculated the permeability, we know that when it is contaminated, the first thing that will be affected is the permeability. The permeability will be reduced whenever this fine material block this ballast layer. So we tested using our large scale testing permeability apparatus for a different contamination index 0, 25, 50, 75 and 100, and calculated the permeability value of that. You can see here, even when you are having a contamination of a 25%, the permeability is reduced by 90%. When it reaches 50, it's almost 99% of the permeability is compromised and reduced. So this is a serious issue. Like this is where the maintenance come into play very frequently. So here you can see for the various the contamination level that we tested, you can see from in this diagram, starting from here, the top layer, and this here is the lower layer. When you are increasing this contamination level up to 100%, this clearly shows that how much the ballast particles are clogged with these fine particles, which is a serious problem. And we thought of giving a solution for the railway engineers, doing this permeability test and finding how much this material is contaminated is not an easy task. Doing a permeability test in a laboratory is not that easy task. So we thought of what we can come up with a smaller test, simple test, and that way we can decide whether we need to clean this rail track or not. So for that, we come up with the 2D numerical model. Based on these results, we created or developed this numerical model for various levels of fouling in this in the track system, like in the shoulder ballast system and the middle ballast layer. We introduced different levels of contamination to this and check this the drainage capacity. The drainage capacity we use used with a critical drainage capacity. This critical drainage capacity is basically based on the rainfall of that area. So when we know this rainfall of a particular area, we can come up with this critical drainage value. Then by doing many different number of permeability tests in the laboratory based on this Trasagis and Patent 1967 criteria, and using this numerical model for this various layer, we come up with the criteria. For that criteria, we use 3 different models. The first model is when 2 layers of this ballast layer is contaminated, or if you divide into 3 layers. And what happened, if you are having a separate layer called this shoulder ballast layer, when this is contaminated, what happened? And based on our results, the railway engineers can collect one sample from the site and simply do the particle size analysis. No need to do the permeability test. High-end, those are, it's not very easy, especially for the large scale testing. Just doing one simple sieve analysis test, come up with how much of a contamination is there on the particular layer. And by using this chart developed for, as I said, this QC value. Whenever you are dealing with a different track, you can come up with a different QC value and make a different chart for that particular rail line. Then based on this value here, your Q over QC and the contamination value, you calculate this Q over QC ratio. Then where this your Q over QC ratio is coming, that will tell you whether you need a maintenance work. Do you need to clean the ballast or not? Okay. So this model 1 and the model 2, the model 3, based on our finding, this model 3 is the very critical one because of this layer here. Because the water is like once come to the the rail system during the heavy rain time, the water try to leave the track on the lateral direction. So this layer, when this layer is contaminated highly, where this entire track system is damaged, or we can see derailment and lot of damages. So this our study shows that the third model with like a when the engineer wanted to check the conditions of the rail track, they can take one sample here, one sample here, one sample on this level, one sample, 4 different samples, just run this particle size distribution and come up and find this Q over QC value. Wherever the Q over QC value is fitting, that will give this criteria of whether they need a clean or maintenance required or not. So based on the Q over QC value, if the Q over QC value is very high, you don't need maintenance, or it was already good drainage. But wherever you are having a very poor, a very low Q over QC value, you need to start do this cleaning work. Or somewhere here, it will tell the railway engineers, you have to ready for this maintenance in the coming months. So this type of criterion will help saving time, and also any problem that predictable problems comes in the future related to this maintenance work. The second work, artificial inclusions for rail track improvements. Nowadays, like many researchers are working on how we can improve this rail track for faster and heavier train. So now in Sri Lanka, we are trying to go more than 100 km/h in most of the lines, maybe except the upcountry line. We need a lot of improvement on that side. But whenever we go beyond 100 km/h, that is where we started to face this problem. The degradation, derailment, a lot of problems are there, vibrations. These artificial inclusions, such as the rubber pads, are very much good solutions for these problems. Here you can see there is one artificial inclusions called underslipper pads, which is directly glued to under the slipper. And there is another artificial inclusions called under ballast mat, which is placed below the ballast layer. So these are the 2 different layers where you can introduce and reduce the vibration, reduce the hard contact with the concrete slipper with the ballast, and you can distribute the pressure evenly so that you can minimize the ballast damages. So these things were tested thanks to University of Wollongong, Australia, where I tested, and the idea of building the facilities in our department here came from the experience I gathered from University of Wollongong. You can see a similar large-scale testing apparatus. I was spending about 3 years with this machine. This is a cyclic dynamic actuator, where we tested this underslipper pad and under ballast mat. And this result shows very significant improvement whenever we introduce this underslipper pad. About 20 to 30% of a vertical, 10 to 15% of a lateral deformations, and the reduction of a stress about up to 12%, and especially the degradation or the ballast damage can be reduced more than 50%, which is very much significant. That reduce a significant amount of results you can see here, and also the degradation analysis after the testing. And it is also shown that we tested this, how this interparticle contact after we introduce this rubber pad is making with the railway sleepers. You can see for that we use surface profiler film. It's a thin material where it is in contact with the two material. When it is get pressurized, the material change its color. So you can see here this the paper is directly glued to the concrete, and this paper is glued to this the rubber pad where this ballast particle will come in contact. After the testing of 5,000 loading cycles, we see here this very discrete contact. Whereas when you introduce this rubber, this area of contact is significantly distributed. So this clearly tells that how hard this material with the concrete, the ballast material with the concrete, when you are having a discrete contact, and when we introduce this rubber, how that evenly distribute. Again, like the other material, this under ballast mat, we place under this ballast layer, the bottom of the ballast layer, which is specifically used for rail track running on bridges or railway tunnels, where your formation or underneath the ballast layer is very much stiff. So where we are introducing this under ballast mat, we have already tested these materials in rail track in New South Wales, and we have seen significant improvements in terms of ballast maintenance. So here also we can see a significant percentage reduction in the vertical and lateral deformations, as reduction in stresses, and also the ballast damage or the particle degradation. Then we have this rubber going on the top of this ballast layer, and the rubber going the bottom of the ballast layer. Why not rubber in between or in the ballast layer? So we thought of that, and we introduced this testing, include these rubber particles to this ballast. So what we did is we take these waste tires, especially these large size tractor tires, where we can cut like almost size of this ballast layer, similar to that shape. And we put it into the ballast layer, mix it with that, and we tested various things, shear and degradations. And also we model this one in the discrete element model. This is, one of the great tool for this type of a ballast material, where the granular discrete materials can be easily modeled in the discrete element model rather than this finite element model, where it is a very continuum model. Most of the time is not suitable. So we come up with this, the results. You can see here this the discrete element model. Basically, what we do is like we take this realistic ballast particle, do it with the 3D scanning, and take this 3D scan particle as a CAD particle to the program, and the program will deal with exactly the ballast particle. So that's the speciality of this discrete element model. So we are testing in numerically the actual particles. So based on that numerical and the laboratory testing, and we found that when we are introducing 10 to 15% shredded rubber by weight to this the ballast layer, we can reduce significant amount of degradation, even though there is a little bit of a compromise for the direct shear or the shear resistant. As we know, these rubber particles are less stiffness than this ballast particle. That will reduce the shear resistance, but in terms of a degradation, we can significantly bring down the degradation level. Then we have already this rubber pads tested for under slipper pad and under ballast mat, working good. And in our recent project where we received a 40 million research grant from the World Bank, it is a AHEAD project. We just completed 2 years ago. On that project, we come up with this modifying this under slipper pad using this novel grid USP. Like we know that the geogrids are used in civil engineering projects. So we thought, like, why not mimicking this geogrid into the rubber and make this rubber as a kind of a geogrid plus rubber type of a material. And we come up with this new material, and we also applied already patent and is in progress now. And we tested this material, this the grid underslipper pad. We tested in the laboratory with the various sizes, various aperture openings and spacing. We tested 9 different sections, and you can see here synthetic rubbers that we used in the laboratory for testing. Not only this synthetic rubber, we also tested some of the recycled rubbers, where these recycled rubbers are made from the making the granulates of the waste tire and making into sheets of rubber. And from that rubber, we made this the grid underslipper pads. The test results is a promising one. You can see here the grid underslipper pad, that significantly increased this the shear resistance compared to the plain rubber. We can see it is increasingly increasing this the shear strength of this ballast layer. And for the various the sections or the cross sections we have tested, we can see here the when we increase the aperture size, we have this shear strength goes higher, but there is a limitations. We cannot make the opening as large as we want, because once we make the openings as large as possible, then we are losing the rubber, which we need to distribute the load and make the material surface kind of a cushion. So we cannot go like more and more sizes. Then we need to check, like, how that is impacting the ballast degradation, how much it is going to damage this ballast layer. So we tested that one also, the ballast degradation, and come up with two different sizes, which is like a grid USP and 30 aperture size with the type 2. You can see here this one, type 2 30. This one is working well in terms of increasing the shear strength and reducing the degradations. So this is the one we propose that in our innovation, this type of grid underslipper pad can be used instead of underslipper pad, both to increase the shear resistance and also decreasing the degradation. So this result shows that our findings. And also we at the same time we tested 2 different materials, the synthetic material and also the recycled material, which is always good using a recycled material for any infrastructure development. So we found that the recycled materials also working very well in terms of performance of this rail track. Again, we put together these all things to this discrete element model. 3D scanned a lot of ballast particle representing this the ballast layers, and put it into the CAD and and change into a DEM elements of for the softwares. And many different models we tested, and giving our laboratory findings are coincide with this numerical analysis. So that this type of testing, doing it in the laboratory is take a lot of time. So if we can simulate these things in the discrete element model or numerical models, then we don't need to do many number of tests. After doing some tests, we can extend further with this numerical model. So that's we did on this study, and come up with that the findings are good even for the higher stresses. We also test this the grid underslipper pad in our large scale cyclic load apparatus, where we apply cyclic loading, which is very much similar to when the wheel is rolling on top of this rail. Basically it's a sinusoidal waveform. So we can apply this sinusoidal waveform in our recently built this cyclic apparatus. And for that, we made this unit cell of a real rail track in the laboratory, and we tested this grid underslipper pad, and found that even in the cyclic loading also, we see there is a significant reduction in the lateral deformation, which is why we put that grid, because we want the track to be not to laterally slide. If laterally slide, then you will be getting a derailments. So this grid underslipper pad is significantly reduce this the lateral sliding, and can be used in rail track. And again, we tested the ballast breakage after the cyclic loading test, and see that this again this the rubber pad grid underslipper pads are working very well. Then in my last the research work, nowadays AI is everywhere. I mean, take any field, AI is there. Neural network model. What we did is like this DEM analysis, what we are running in the laboratory. We have a supercomputer which is having like something around 48 processor. With that 48 processor, sometime it takes like 5 days to run one single test, because that much this numerical analysis taking time. So why not the use of artificial intelligence to cut down this numerical analysis work, where we can come up with the model to connect the DEM to the artificial neural network. Then instead of running this DEM for 5 days, within like a 5 seconds, your artificial neural network give the results. So this project recently my students worked on and come up with this model, artificial neural network model, where how these particle shapes, these ballast particles comes with various shapes, rounded, more elongated, highly angular. How these particle shapes going to affect this this performance of this material. For that, we have tested many different the shapes. There are many different shapes index that we come up with: elongation index, flatness index, aspect ratio, convexity index. With that index, we develop a DEM model for that. And at the same time, we also feed the data from the DEM model to the ANN to come up with this model in the ANN and develop, instead of doing a DEM model for 5 days and a simple ANN run will give the data that you are required, especially this frictional resistance of these ballast materials. Here you can see this our ANN model fitting very well with having R squared of more than 0.9, which is a very good number. And we develop this applications where you give this a sample particle shape characteristic, and your ANN model will give the shear resistance and the void ratio of that particular ballast set, which is very, very good, because running a shear test or a DEM test take number of hours, labor intensive works. But this ANN model quickly tell us what type of the shear resistance or the friction angle that we are looking at. So a kind of initial work we can use this one. So that's all our recent work, and our recent works are published in many journals. I have published more than 50 research publications, including about 12 high impact journals and more than 30 conference papers. And we also applied for the patent for this grid USB, already in progress with the NIPO. We are also having a collaboration with the Sri Lankan Railways engineer Nuwan Amarasena. I always call him for any help. we also had a discussion with them when they visited Pereira year back. And we are closely working with this Sri Lankan Railways. And one of the things that I wanted to happily say that one of the my former student, currently a lecturer at the University of Rugana, engineer Dr. Sushan Mayuranga, completed his PhD last year under this head grant. The novel grid USP that we come up with is from his research work. We are also collaborating with the University of Rugana. Nowadays, University of Rugana students are coming all the way to Pereira and using the facilities that we developed and doing a lot of railway testing. So we still, collaborating and working. And engineer Shehan Vanigasegara, who was my undergraduate project students, where he worked on my initial time of my faculty. He was in my project. He was of my project students. Now he got a job in UK high-speed railway project HS2, very famous mega project. Just having that experience in the railway project when he was doing undergraduate, he secured a project engineer position at this UK HS2 project. So these outcomes demonstrate how the training at the University of Pereira extend its influence on other universities in Sri Lanka and also the major national and the international projects. And we are also planning to introduce the railway engineering courses initially at the postgraduate level and later in our next curriculum revision, if possible, in the undergraduate level, because we need to, make engineers. I never learned anything about railway engineering in my undergraduate time. So I think still, most of our curriculums are not having much of a railway engineering, subject. So we are planning to, include and train our future engineers on these railways. Finally, I would like to acknowledge my sincere gratitude to my PhD supervisor, distinguished Professor Buddhima Indra Ratna, for his invaluable guidance and unwavering support throughout my research journey at the University of Wollongong, Australia. I also sincerely acknowledge the contribution of my current and former undergraduate and postgraduate students whose research works are presented herein. Grateful appreciations to extended to the accelerating higher education expansion and development ahead operations funded by the World Bank, where we received this 40 million research grant that we could able to develop those large scale testing facilities at the laboratory of the Department of Civil Engineering. Sincere thanks to the financial assistance provided by the University of Pereira through the University Research Grant. I have secured 2 research grants so far. The support provided by the Sri Lankan Railways, gratefully acknowledged, and I highly appreciate the assistance extended by the academic and non-academic staff of the Department of Civil Engineering, University of Pereira. And I also wanted to acknowledge the support received from the Penrol, Belgium, where they provided this recycled rubber material sheets from the Belgium. Thank you very much.
Thank you very much, Dr. Raja, for your highly informative and exciting research work. We have our former GMR, Pereira Silva, and our is the transport sector chairman also. We would have been highly impressed with your work. Having said that, now I cordially invite our President-elect, Engineer Kosala Kamarodenia, and Engineer Mandasila Chairman, Civil Engineering Sectional Committee, to the stage. To give away the token of appreciation to Dr. Nawat Raja. Our final item is word of thanks. Before that, I think I had to appreciate or welcome Professor Yoi Pereira's own son, Mr. Lawrence Pereira, and his wife. Mr. Lawrence has been continuously communicating with me for almost 1 year to fix the date and to plan his journey to Sri Lanka. He came all the way from Australia. Thank you very much. And our vote of thanks will be read by Engineer Mangal Silva, Chairman, Civil Engineering Section. Over to you.
Good evening, dear ladies and gentlemen. First and foremost, I would like to extend my sincere gratitude to today our resource person, Dr. S.K. Nawat Raja. Thank you very much for your very informative oration today. It's really wonderful. Thank you very much, sir. Then I want to really appreciate the family members of late Professor Yoi Pereira. Thank you very much, Mr. Lawrence and your wife. Thank you very much. Came here from all the way from Australia and present here. We really appreciate, we consider it as a great motivation to us. Then I can see Engineer Professor Kushan. Actually, he's the head of the Department of Civil Engineering, University of Pereira. Thank you very much, sir, for your presence. Thank you. I really appreciate it. Then I want to extend my sincere gratitude to our past presidents. We have very senior past presidents here. Actually, we're not talking about the railways. We have Engineer P.R. Silva. He's the, according to my knowledge, he's the most senior railway track engineer in the country. Thank you very much. Thank you very much. Also, Engineer P.R. Silva is with us. Thank you very much, sir. Also, I really want to appreciate, although he's not here, our president, Engineer Daniel Jalat, because he did a lot of work to organize this event. Actually, he had a continuous discussions with the Dean, Faculty of Engineering, University of Pereira, and also with the head of the department for selecting a very suitable person to do this oration. Actually, we can see that the reality of the results and everything what he has done. Thank you, Engineer Graniar Jalat. And also I like to appreciate Engineer President-elect Kosala Kamburadeniya for your kind support and kind assistance to do all the proceedings today without any difficulty in the absence of our president. Thank you, Kosala. Then, my dear council members, I really thank you. I mean, you did a lot of things. I mean, you are the people, those who approved this event and all the events and so many things. Thank you very much for your kind support. Thank you, my dear council members and my civil engineering section committee members. You are the people who organized this event. Thank you very much. Then we have our Executive Secretary, CEO, Engineer Neil. Thank you, Neil. And actually, I want to say thank you very much to his staff members. Actually, they are the people who are the backbone of this event. Thank you very much. at last not least, all the participants here, I can see very senior members from University of Pereira. Thank you very much. Unless your participation is here, we couldn't do this oration. Thank you very much for your participation. Not only that, I cannot forget the participants, those who are online. There was a huge enthusiasm actually from the day that we send our flyers. They wanted to ask the link. So from the other countries, thank you very much, my dear participants, those who are in online. At last, I have a kind request for all of you to join the fellowship at Members Lodge. Thank you very much. Good night. Have a pleasant evening.